1.3, arcs, chords, and central angles. The image shows a circle with two congruent chords. Okay, so the two congruent chords we're talking about, we've got DE is congruent to CB. Draw the central angles associated with the highlighted arcs from D to E and B to C. So the central angles that subtend these arcs is what they're really trying to say. Associated with, they could also say that subtend. So, all right, we can see that this angle here, DAE, just to make it clear, angle DAE subtends arc DE. And here we've got angle CAB subtends arc CB. All right, we're talking about minor arcs here, not the major arc also associated with that, that chord. Okay, how do the measures of the two central angles appear to compare? Prove that this observation is true. So how do the measures of the two central angles appear to compare? I guess they're talking about this angle and this angle. I mean, I'm no dentist, but those look like those angles appear to be congruent. They appear to be congruent. I say that comment. I know maybe that doesn't make sense to you. To be a dentist, part of the test is you have to like look at an angle and tell how many degrees it is. So if that's a profession you're looking to go into, start practicing now. Okay, so I want to prove that this observation is true. Okay, so I've got this arc, this side right here labeled with a 1 dash. So I imagine I'm going to probably have to label some more stuff in this diagram. So if I'm thinking about all these line segments I just drew, well, how do we classify all of these segments? EA, AD, CA, and AB. Well, these are all radii. Right, they start from the center and hit the perimeter, the circumference. That means they're radii. And we know that all radii of a circle are congruent. So I can label these all with 2 hash marks. Great. Now I know by what postulate it's telling me that these two triangles are congruent. Well, I know by SSS that triangle ADE is going to be congruent to. So I went from the angle to 2, 1, 2. So angle to 2, 1, 2. And I guess you could actually, since it's isosceles, you could go ABC or ACB. Let's sort of trace it out. The original went from ADE, so let's do ACB, just to look sort of symmetric. But you could technically say ABC, and I think that would be just as valid since they're isosceles. Okay, so how is this going to help us? If I know these triangles are congruent, why would that then in turn tell me that these two angles are also congruent? Yeah, well, it's those 5 letters, right? C, PC, TC. Corresponding parts of congruent triangles are congruent. That tells me that angle DAE is congruent to angle CAB. All right, great. I didn't really do a formal proof, but I didn't really have a ton of space, and I didn't want to shock any of you too much. 3. What does this tell you about the measures of the highlighted arcs from D to E and B to C? Explain your reasoning. What does this tell me? Well, I don't know if there's a formal proof that would be applicable here, but here's what I am thinking. If I've got an angle here that's subtending an arc It's going the same distance in both directions, and it's opening at the same measurement of an angle. This arc is going to be a certain length. And basically all we've done is like rotate this, or this central angle here. If I wanted to like bring it over to where ABC was, it's really the exact same thing. So if these two triangles are congruent, I would guess that it makes sense that the arcs that they subtend also are congruent. So what I'm trying to say here, and I can't really show the diagram and say what I'm saying at the same time. If central angles are congruent, the arcs they subtend must also be congruent. In other words, DAE is congruent to CAB, so arc DE should be congruent to arc CB. Or I could also write the measure of arc DE is equal to the measure of arc CB. All right, so that's my reasoning, right? We've really just taken this arc and rotated it. We haven't, changed however wide or narrow the angle is. So why would the length of this arc change at all? It wouldn't. It would be the same. Okay, are you ready for more? Prove that the perpendicular bisector of a chord goes through the center of a circle. Okay, so yeah, it's not a bad proof at all. Let me just where's my compass? There we go. Okay. So just draw a quick diagram. Circle. This is actually a rather important proof. I'm not going to do a 2-column proof, but it deals with topics we've already learned about this year, and I've definitely actually seen this be on the Regents before. Not that you guys have to worry about that, but it's a topic that if you do plan to take the Regents one day, it could definitely be on it. So let's call this chord AB. Okay, so I want to prove that if I were to construct a perpendicular bisector of this chord, it would cut through and hit that right in the center. And it sort of looks like it's true. So what I'm going to do, let me use another color. I'm going to do exactly what I did in the last problem, and I'm going to draw the central angle associated with this chord. So, because we have a 2 radii here, right, that's the center, I know that since all radii are congruent, those 2 line segments must also be congruent. So what kind of triangle do we have here? This is an isosceles triangle. Well, what do we know about isosceles triangles? We know that the angles opposite the congruent sides must also be congruent. That's one thing we know. Okay. What I'm going to do next is, might look like cheating, but it's totally a valid part of a proof. What I'm going to do next is I'm going to draw a line segment, and I'm going to state that it is the bisector of line segment AB. So let's call this CD. I'm going to say construct CD so that it bisects line segment AB. And that's allowed. I'm not saying that it bisects it and it's perpendicular. That would be saying too much. That would be saying 2 things. If I'm going to do a construction, I can say one thing that's true about it. I can say there must exist some line that cuts it in half, so that's the one I picked. All right. Now we also see right here, we've got 2 triangles, right? So anytime you see 2 triangles in a diagram, you're probably going to want to prove they're congruent. And we can do that right here using side, angle, side. you could also see it another way, right? If we use the reflexive property, we'd actually have side, side, side. We could prove that it's congruent in a couple different ways. So if we know that these two triangles are congruent by side angle side, we say that triangle ADC, right, ADC will be congruent to BDC by side angle side. By CPCTC, we know that angle ADC is going to be congruent to angle BDC. Right, obviously, if these two triangles are congruent, the corresponding angles must be congruent as well. So let me label those in purple so they really stand out. Okay. Well, you'll notice that these two angles lie in a straight line, so they're supplementary. They're also congruent. So if two angles add up to 180 and they're congruent, what has to be the measure of each angle? All right, 90. 90 plus 90 is 180. So when two supplementary angles are congruent, they must have measures of 90. All right, so if they're both 90, that means we've got right angles here. And I've created not only a line that bisects the line that chord AB, it's also perpendicular to it. Okay, so we've shown that it's always going to be a perpendicular bisector. And I can quickly do that down here. Right, this is a chord, right? It's going from two different points. If I create that perpendicular bisector, you see that it goes right through the center of the circle. All right, so this use of isosceles triangles, like I used it in this proof, I used it in this proof as well, is incredibly important when we're talking about circles. Knowing the radiuses are always equal and looking for these isosceles triangles is going to be very helpful for us this unit. All right, have a great day.